Hi everybody, Namaste and welcome to yet another episode from Murali's World of Physics. 2 days back, there was a news in the media regarding a Singapore Airlines flight which met with a severe air turbulence on its flight from London to Singapore. Which was flying at an altitude of 37,000 feet, suddenly dropped by about 6,000 feet on entering the air turbulence. One passenger died on board and about 70 other passengers were injured to different extents during the incident. It turned out that most of the passengers who were injured were those who did not fasten their seatbelts while being seated on the aircraft in spite of the announcements from the pilot. Now, these air turbulences are not a very uncommon occurrence during flights. I am sure that anybody who had traveled by air at least once might have experienced this air turbulence at least once. But I wonder how many of you would ever have thought as to why this happens and how the air turbulences affect the aircraft. Well, in today's video, I am proposing to explain the physics behind the occurrence of these air turbulences and how they affect the aircraft. But before we go into the details regarding the air turbulences, let's understand how the aircraft is able to fly in the air. Now this shows an aircraft flying in the air. Well, an airplane flies because of the presence of air in the atmosphere of the Earth. For example, the plane cannot fly on the moon since the moon does not have air surrounding it. In order to see how the air helps an airplane fly, let us first look at what are the forces operating on the aircraft when it is flying. The most important force on the airplane is the gravitational force. W is equal to mg. M is the mass of the aircraft and g is the acceleration due to gravity. So that is the gravitational force acting on the aircraft, which acts vertically downwards. The next important force is of course the thrust developed in the engine and denoted by F, which is the force which is responsible for the forward motion of the aircraft. Thirdly, we have the drag or the resistance due to air, which is acting in a direction which is opposite to the direction in which the aircraft is flying. And finally, we have what is known as the lift, which is acting upwards in a direction opposite to the direction of gravitational force. So these are the four distinct forces which are operating on the aircraft when it is flying. So let us see how each of these forces arise. Firstly, the gravitational force W is equal to mg. This arises as per Newton's law of universal gravitation, which states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This force is operative universally on all bodies, from the apple that fell on Sir Isaac Newton's head to the distant gigantic galaxies of the universe. The expression for this force as given by Newton is G is equal to m1 m2 by r square. m1 and m2 are the masses of the two objects and r is the distance between the centers of these two objects. So each body attracts the other body with a force given by the same expression. So these two forces are the same. In fact, these are called action and reaction and they are equal as per Newton's third law. So G is the gravitational constant whose value is equal to 6.674 into 10 raised to minus 11 meter cubed per kilogram per second squared. This gravitational force of the earth is manifested as the weight of the plane. It is an omnipresent force and always tries to pull down the plane towards the center of the earth. The second force is the thrust F, which is the force developed by the engine to keep the aircraft moving in the forward direction. So it is the main force which is responsible for the onward motion of the aircraft to its destination. The effect of this force as in the case of any other force, is to provide an acceleration to the plane. So this is as specified by Newton's second law. F is equal to m into a, where a is the acceleration developed in the body and F is the force applied. So the acceleration developed is proportional to the force applied and inversely proportional to the mass of the object. Here, the aircraft. Now in this context, we have to distinguish between two types of aircraft engines. The first is known as the propeller engine. So here these have propeller blades that spin at high speed, just like the blades of a domestic fan. So we have the blades here. This provides a pressure gradient across the plane of the blades and exerts a force on the plane in the forward direction, and that is the thrust. The propeller works by displacing the air, pulling it behind itself. This is the action. And this movement of air then results in the aircraft being pushed forward from the resulting pressure difference. And this is the reaction in the opposite direction. And numerically, these two will be equal. According to Newton's third law of motion, action and reaction being equal and opposite. The second type of engine is the jet engine. Here, the air from the atmosphere enters the front intake and is compressed, and then the air is forced into combustion chambers where the fuel is sprayed into it. The mixture of air and fuel is ignited, and the gases that are formed as a result of the burning of the fuel and air mixture expands rapidly and are exhausted through the rear of the combustion chambers. Provides an equal force, that is the thrust, in the forward direction on the airplane. Now this is a schematic diagram of the jet engine. We have the air intake from the front. This is compressed and mixed with the fuel in this section, and the mixture is ignited in the combustion chamber, whereby the gases formed as a result of the combustion expands rapidly, and because of the immense pressure developed, this is thrust outwards through the exhaust in the backward direction. So this provides the action, and as a result of this action, there is a thrust in the opposite direction on the aircraft, that is a reaction. So as a result of this thrust is developed and the airplane moves in the forward direction. In both the cases of the aircraft engines, the force, that is the thrust developed and applied on the aircraft, is specified by the rate of change of momentum of the aircraft. So F is equal to d by dt of the momentum mv, that is equal to dp by dt, and this follows directly from Newton's second law. The third type of force that we consider is the drag D, arising from the resistance offered by the air surrounding the aircraft. This drag force results from the frictional forces between the surface of the aircraft and the layers of the air surrounding it. Friction, as we know, is the force that one surface exerts on another when the two rub against each other. That is, when there is relative motion between these two surfaces. The characteristic property of friction is that it always opposes the motion, which is the root cause of that force itself. The friction between the aircraft and the air broadly depends on the reactional force that the air exerts on the aircraft. This reaction is equal and opposite to the weight of the plane. So R is equal to, the reaction is equal to m into g, where m is the mass of the aircraft. This is nothing but the weight of the aircraft. Now, the drag is proportional to this reaction R, and the proportionality constant is what we refer to as the coefficient of friction. It is defined as the ratio of the frictional force to the normal reaction. So mu is equal to d by R. If you want more details on frictional forces, kindly watch my earlier video, whose link is given here, on Murali's World of Physics. Now, the last force acting on the airplane is the lift L. This force is a mechanical aerodynamic force acting on the plane in motion through air. It is generated by every part of the airplane, in fact, but most of the lift on a normal airliner is generated by the wings. In order to understand the origin of the lift, let us first understand the two terms streamlines and aileron. Streamlines are imaginary lines in a moving body of a gas or liquid.
These illustrate the direction of fluid velocity at every point in the flow field. The velocity vector at each point along a streamline is tangential to that line. So this diagram illustrates how the streamlines are shaped. So this is a object which is moving through air or any fluid for that matter. So when it is moving through air, the air or fluid, the fluid around it gives way to the object by bending around the front tip, and then these join together at the back. These lines are called the streamlines. So the velocity at any point will be tangential to the line at that point. In steady flow, the streamlines do not change over time. The pattern of the streamlines remains constant as long as the flow conditions remain unchanged. Of course, if the conditions of flow change, the pattern of the streamlines also will change correspondingly. In steady state flow of the fluid, streamlines do not change over time. Also, the streamlines never intersect each other. This is because if they do intersect, then at the point of intersection, it means that the velocity have two directions tangential to the two lines which intersect, and that is not possible because at any point the velocity can be only in one direction. So therefore the streamlines never intersect each other. Considerations of friction tells us that an object moving through a fluid must have a streamlined shape in order to minimize frictional forces acting on the surface of the object. Now such shapes are characterized by smooth, rounded forms that allow the fluid to flow over the surface with minimal disruption and thereby causing minimum friction on the surface of the body. Usually the front end is typically rounded to gently divert the fluid around the object, reducing pressure drag, and the rear end tapers to a point or a narrow edge, helping the fluid to smoothly close back in behind the object. In our present case, the overall shape of the aircraft is designed to have streamlined structure, specifically the shape of the two wings. The cross-section of the wings is called an aerofoil. So if you take either of the wings, the cross-section of the wing perpendicular to the length of the wing will be something like this. So it is rounded in front and tapered at the back. So this shape is called the aerofoil. So this illustrates the streamlines around an aerofoil. Now lift is generated by the interaction and contact of a solid body, in our case the aircraft, with a fluid. Here the fluid is the air surrounding the aircraft. The origin of lift can be explained by the principle known as the Bernoulli's theorem. In a steady, incompressible and frictionless fluid flow, the sum of the pressure energy, kinetic energy per unit volume and the potential energy per unit volume remains constant along any streamline. So that is the statement of the Bernoulli's theorem. So in order to illustrate the Bernoulli's theorem, we consider a section of the fluid which is flowing in this direction. We take a particular section, the areas at the ends of the sections are A1 and A2, the pressures at the start is P1 and at the end is P2, and suppose at the beginning the height above occurrence level is Y1 and the height at the other end is Y2, and the velocities are V1 and V2. Then from the statement of the Bernoulli's theorem, it will turn out that an increase in the speed of a volume of fluid occurs simultaneously with a decrease in either the pressure or the height above a given reference level. Total energy of the fluid per unit volume will remain a constant. So the Bernoulli's principle is in fact derived from the principle of conservation of energy. So this requires that the sum of the kinetic energy, potential energy and internal energy, well, this is the pressure energy, remains a constant. In mathematical terms, one can write P1 plus half rho V1 square plus rho g Y1 is equal to P2 plus half rho V2 square plus rho g Y2, and on dividing by rho g on either side we get P1 by rho g plus half V1 square by g plus Y1 is equal to P2 by rho g plus half V2 square by g plus Y2. In other words, pressure head plus velocity head plus potential head, that is equal to the total energy per unit weight. So all the terms here have dimensions of a distance or length. So that is why each term is known as a head. So this is the pressure head, this is the velocity head, and this is the potential head. So the sum of these quantities is equal to the sum of the same quantities at the other end of the fluid section. So from this it follows that if there is a portion with a higher velocity, that will correspond to a low pressure, and vice versa. That means a portion with a lower velocity will correspond to a higher pressure. So this pressure difference, this will result in an unbalanced force from the high pressure side to low pressure side. So this is precisely what happens in the aircraft. So this is just an illustration of this fact. So we have a object on either side of which there is a pressure difference P1 and P2. Suppose P1 is greater than P2. Then there is a force acting on this body in the direction of decrease of the pressure. So the lift is equal to the area of the surface exposed multiplied by the difference in the pressure. So this is in fact what happens in the case of the aircraft. So this is our aerofoil. These are two typical streamlines. So one can see that the length of the streamlines is different on the lower side as compared to that on the upper side. So the velocity will be more on the upper side as compared to the velocity on the lower side, and therefore there is a pressure difference. There is a high pressure on the lower side and a low pressure on the upper side, and as a result there is a upward force acting on the aerofoil. Now an important parameter which is decisive in determining the amount of lift produced is the so-called angle of attack, shortened to AOA. What is this angle of attack? It is defined with reference to the chord line, which is an imaginary straight line from the leading edge of the aerofoil to the trailing edge. So it is the angle between this chord line and a reference line which is taken as the relative wind direction. Typical values of this angle of attack is around 15 degrees. The angle of attack is a crucial parameter in aerodynamics as it is significantly affecting the lift and drag forces acting on the aircraft. So the angle of attack is directly related to lift generation. As this angle increases, the lift produced by the wing also increases up to a certain point. This angle is also important consideration as far as the air drag is concerned. So these two are related in fact. Now here there is a comparison of the flight conditions and the corresponding effects with regard to the four forces acting on the airplane. So now, as I mentioned, for a steady motion at a given altitude, it is important that the horizontal forces balance each other and the vertical forces also balance each other. So if there is a difference in these pairs of forces, let's see what happens. Suppose the lift is greater than weight. Naturally, the plane will rise because there is an unbalanced force in the upward direction. On the contrary, if the weight is greater than the lift, the plane will fall. So this takes place when the plane is landing, and this condition arises when the plane is taking off. Now, what about the thrust and drag? If the drag is greater than the thrust, the plane will slow down. So that is the situation, for example, when the plane is landing, because the speed has to be reduced, and therefore the drag force overcomes the thrust, and the plane will be decelerated. On the contrary, if the thrust is more than the drag, the plane accelerates. So this is the situation when the plane takes off. So it is natural that the lift should balance the weight while the thrust should balance the drag for the plane to keep itself in the air at a given altitude. If this balance between the pairs of forces is affected in any way, the stability of the aircraft will be affected. It can pitch, roll or drop down in height. Now let us address the question of what are the air pockets and how they affect aircrafts. Air pockets and air turbulences are phenomena that can affect aircraft during flight. Air turbulence refers to the irregular and often violent air motion characterized by rapid changes in the wind speed and direction. There are essentially four types of air turbulences. The first is the clear air turbulence, CAT. This occurs at high altitudes in clear skies, typically near the jet stream. Secondly, mechanical turbulence. This is caused by obstacles such as mountains or buildings which disrupt the airflow. Thirdly, we have thermal turbulence, which is caused by rising warm air due to uneven heating of the Earth's surface. And lastly, we have the wake turbulence, which is created by the passage of another aircraft nearby, especially large ones like jets. The term air pockets is a colloquial expression commonly used to describe sudden, unexpected drops or rises an aircraft experiences during its flight. These are actually specific forms of air turbulences or variations in air pressure that cause these abrupt altitude changes. Now, what are the effects of these air pockets on the aircraft? Structural stress. Prolonged or severe turbulence can place stress on the aircraft structure itself. But of course, modern aircrafts are designed to withstand significant levels of turbulence. Next, flight path deviations. The pilots may need to alter the flight path in order to avoid turbulent areas, which can lead to longer flight times and increased fuel consumption. Now, passenger and crew safety. Turbulence can cause injuries if passengers or crew are not properly seated and secured. It can also cause unsecured objects to become hazardous. And there is a increased workload on the pilot. So, turbulence requires more active control by the pilots, increasing their workload and potentially causing fatigue to them. Now, what are the effects on passengers? Sudden altitude changes. So, the aircraft may experience abrupt changes in altitude, which can be uncomfortable for passengers. Discomfort. Passengers might feel a momentary sensation of weightlessness or a jolt, which can be disconcerting. Now, there is also potential for injury. If the passengers are not seated with seatbelts fastened, they might be thrown from their seats, leading to injuries. Of course, this is precisely what happened to most of the passengers who were injured in the recent accident involving the Singapore Airlines aircraft. Now, what are the precautions that can be taken what are the precautions necessary for situations involving the air pockets? The pilots can use weather radar and reports to identify and avoid turbulent areas. The airlines should plan their flight routes according to the non-turbulent zones. That means avoiding the turbulent zones. Of course, the pilots can change altitude to find a smoother air layer. The communication with air traffic control is very vital. Of course, throughout the flight of the aircraft, the pilot can communicate with other aircrafts also to share information about turbulence encountered along their flight paths and then take necessary diversion of their routes. Of course, passengers are always advised to keep seatbelts fastened while seated to prevent injuries during unexpected turbulences.
If you like this video, kindly click on the like button and then share with your friends and relatives and also with your different groups. If you have not already subscribed to my channel, World World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos. Goodbye.